In this video series, we are talking about statistical inference. And in the next few videos, I'm going to introduce you to two of the most important inferential methods in statistics. The first of these is hypothesis testing. What is a hypothesis? It's just a guess. In the scientific method, we begin with a guess, and a hypothesis is a guess. A hypothesis about a population parameter is a guess of the value of the parameter. For example, if I want to know a population mean, I could start off with guessing what that parameter, the mean, is for that population. Our guess can be based on prior knowledge. For example, the GRE was developed to have a mean of 150. So when the GRE is administered to students, it's reasonable to guess that the mean for the population of all students is going to be 150. Our guess can also be based on a research hypothesis. Suppose we propose that studying for the GRE will increase scores. Well, if students enroll in test preparation before taking the GRE, it's reasonable to guess that the mean for these examinees will be greater than 150 because we're proposing that studying for the GRE will increase scores. We know that without studying for the GRE, the mean is 150. So if they study, we can propose that the mean will be greater than 150. When we conduct a hypothesis test, there is a very distinct series of steps that we must go through. We're going to talk about those steps now, starting with the first one, to postulate a hypothesis about a parameter. We call this the null hypothesis. Imagine that we want to study the effects of GRE test prep with a sample of 64 students. The GRE was scaled to have a mean of 150, so let's use that as our guess, our hypothesis. We're going to propose that the mean, and we're talking here about the parameter, the mean, which is unknown, not the sample, which we can know. The mean is 150 for the population. That's our guess. We call that the null hypothesis, and we symbolize it as I have done here with an H and a subscript O. The second step is to use the null hypothesis to create the sampling distribution for the statistic that we will use to estimate the parameter. Well, what statistic am I going to use to estimate the population mean? I'm going to use the mean of my sample. So what we're interested in here is the sampling distribution of a mean. You'll recall that a sampling distribution is simply a distribution of a statistic when we take samples over and over and over again from the population. The central limit theorem tells us that if our sample size is big enough, and by big enough, statisticians usually mean at least 30, the distribution will be normal. Well, in this example, we have 64 students, so the distribution, the sampling distribution of the mean should be normal. The mean and standard deviation of a sampling distribution of the mean are known. Mathematical statisticians have figured this out for us. And here's what they have figured out. That if you take all possible samples from the population of a certain size, say n, that the mean of these sample means will be the same as the mean of the original distribution of scores, in this case GRE scores. The standard deviation of all these means is actually going to be less than the standard deviation of the original scores. It's going to be the standard deviation of the original scores divided by the square root of n. So for our example, where we have 64 students, this is the way the sampling distribution would look. I have drawn here a distribution that has a mean of means of 150 and a standard deviation of means of 8.75, the original standard deviation of GRE scores, divided by the square root of my sample size, 64. That gives me a standard deviation of means of 1.1, which is a whole lot less than the variability of the original scores, which had a standard deviation of 8.75. The next thing we do is set a level of confidence. How confident do we want to be in our answer? The industry standard in many disciplines, including the behavioral and social sciences, education, medical fields, is 95%. So we will, for this example, set our level of confidence at 95%. Now let's talk about how confidence relates to errors. When we reject a true null hypothesis, it is called a type 1 error. We're in the process right now of testing a null hypothesis that the mean parameter is 150. At the end of our study, we may decide to reject that, to say our guess is wrong. When we reject that null hypothesis, if the null hypothesis is true, if in fact we made the right guess, but then we throw it out, we reject it, we call that a type 1 error. We don't want that to happen. If the null hypothesis is true, we don't want to reject it, we want to keep it or retain it. So our confidence level that we're going to set is going to be 95%, which means that the possibility of a type 1 error is 5%, or expressed as a proportion, 0.05. Statisticians use the Greek letter alpha to indicate the type 1 error rate that they're willing to live with. So here alpha is 0.05. Notice that if we subtract the error from 1, that will give us our confidence level of 0.95 or 95%. Once we've done that, we now calculate the statistic for the sample. That is, we actually collect the data and calculate the mean. What is the sample mean? Well, let's suppose that in our example, after these 64 students went through the GRE test prep course, that they took the GRE, and the average of their GRE scores was 153. So our sample mean is 153. We then determine where our sample mean, our particular statistic, fits on the sampling distribution. Let's take a look at the picture. Here again is a picture of the sampling distribution when the mean of the distribution is 150. That is, when our null hypothesis is true. Where is the mean that we actually observed? We know that the sampling distribution is simply a distribution of all the possible means. Well, which one is ours? And I've drawn an arrow here to indicate that ours is right here. That is one mean out of these thousands and thousands of means that are depicted in this sampling distribution. It's the mean that we obtained in our one sample. The final step in a hypothesis testing is to make a decision. If the value of our statistic is unlikely, given the truth of the null hypothesis, we're going to reject the null hypothesis. Does that make sense? That is, if we've made a guess and then we make a scientific observation that makes that guess look like it's not a very good guess, we're going to throw out that guess. We're going to reject the null hypothesis. Otherwise, we'll retain the null hypothesis. Well, what I've done here is I have shown the probability with a little slice of red area that we will obtain a mean of 153 or even greater, that is, even more incompatible with our null hypothesis. And that probability is 0.003, very small, less than 1%, less than 0.5%. It's 0.3%. The chance of obtaining the mean that we observed, or a mean even bigger than 153, is less than 0.5% if this is the true distribution we're looking at. And remember that this distribution was created using the null hypothesis. A p-value is a measure of inconsistency with the null hypothesis, and the p-value in our case is 0.003, that little red area that I showed you. P is the probability of obtaining a statistic that is at least as inconsistent with the null hypothesis as the observed value that we have for our statistic, if the null hypothesis is true. And our decisions about the null hypothesis are based on this p-value. When the p-value is very, very small, and what do we mean by that? That it's less than or equal to alpha, which we set here as 0.05, we reject the null hypothesis. When the p-value is bigger than 0.05, we keep the null hypothesis. That doesn't mean we've shown the null hypothesis to be true, but we've considered it a reasonable enough guess that we're not going to throw it out. So what did we have with our data? We had a p of 0.003, and we had set alpha at 0.05. So we will reject the null hypothesis. We will look at this picture and say, if the null hypothesis is true so that this picture represents the sampling distribution of means, then we got a mean that was very, very unlikely to be obtained. It's like winning the lottery. So rather than say we won the lottery, what we're going to say is this picture is not the right picture. This is not really the sampling distribution of means. Why? Because the parameter is really not 150. Rejection of the null hypothesis leads us to accept an alternative hypothesis, something we think is more realistic given our observations. The alternative hypothesis is often a statistical expression of our research hypothesis. If we were hypothesizing in our research that test prep would increase GRE scores, then what we're proposing is for students who have test preparation, they're going to have a population mean that is greater than 150. That is, all the students who take test prep courses, if we put them all together and look at that entire population, the mean of that population should be bigger than 150. And that is in fact what we're concluding here. We are rejecting the null hypothesis of 150 and concluding that the alternative hypothesis is true. Could we be making a mistake? Yes, but we're holding the error rate, that is the type 1 error rate, the possibility of making a mistake, at a maximum of 5%. So I'm 95% confident when I say that the mean for the population is greater than 150.